Hello, business community. So here we go now for calculating the probability of future customer engagement. And as you can see, we're here in a Databricks machine learning environment. We have our Jupyter lab up and running. And I would say, let's dive into the code right now. So, and non-subscription retail models, customer come and go. Yes, of course, with no long-term commitments, making it difficult to determine whether a customer will return in the future. But this is what we want. So determining the probability that a customer will re-emerge is critical to the design of effective marketing campaigns. Different messaging and promotions may be required to incentivize customers who will likely drop out to return to our stores, so we'll lure them back in. Engaged customers may be more responsive to marketing. Yes, yes, yes. So here we go. The Buy Till You Die model, popularized by Peter Fader. Beautiful. I don't know this model, but hey, we're just interested in the code, so let's take what's already done and programmed for us. Leverage two basic customer metrics: the recency of a customer last engagement, so how many days have passed till the customer last bought in our brick and mortar stores or online, and the frequency of repeat transaction over customer lifetime. Yeah, of course, we know how often has he bought something, the quantities, the time period that passed, to derive a probability of future re-engagement. This is done by fitting the customer history to curves describing the distribution of purchase frequencies and engagement drop-off following a prior purchase. Okay, the mathematics behind this model is fairly complex, but it has been encapsulated in the Lifetimes library. So we just implement Lifetime. So set up the environment. We have a Databricks machine learning runtime cluster. We are running this. This is here. Beautiful. As you can see, my cluster here is at Tom 7. So XLRD, this is an old one. We can install XLRD, no problem. Then NB convert, and then we're gonna install Lifetimes. Yes. So wait for this to finish. Yes, beautiful, beautiful, beautiful. So let's load a sample data set. Of course, we need some data set, and there we have some online retail data set. So we just click the link on retail data set, and we have a Microsoft Excel workbook. We're to our local file system. Yes, this is done. Upload and access it here. I already did this for you. So if you want to have a look at the data, here we have now a Databricks file system. And in the file store, not so fast, I have now online retail, and there I have my online retail XLSX file already uploaded. You just say upload, you upload the file, and there we go. So if you use the Databricks utility for the file system, and you just want to get the path, here we have it, the Databricks file system, file store tables. Then I did an online retail directory, and here is our retail XLSX file from our online retail dataset that we downloaded. So now I install pandas, and I install a little bit more advanced Excel, read Excel routine. This is Open Python XL. And then, because I want to make the life easy for me, I copy it just to a local file system. And what we do is simply we define a schema, and we say, hey, panda, read Excel file, my temporary Excel file, the sheet name, online retail, the header is 0, and the order scheme is this one here. So as you can see, we just wait for the command to finish. Running command, and what we should end up with is simply a panda data frame, an orders panda data frame, invoice number, stock code, the description of the item, the quantity of each product per transaction, the date, the price in pound, the customer ID is simply a 5-digit number, and the country where each customer resides. And then we're gonna explore the dataset. To enable the exploration using SQL statements, let's flip the Panda data frame in a Spark data frame. Oh yeah, of course. But first we have to have the data frame. So come on, it is not that complicated. So let's look at a head of our Panda data frame. We have, as I told you, the invoice number, the stock code, the description of whatever the object is, the quantities purchased, the invoice date, the unit price, the customer ID, and the country of residence. So here we go. And now we explore the dataset. So the first thing we do is say Spark, create data frame from a Spark. From a Panda data frame, we have now a Spark data frame. And we create a view. So this is exactly what it is. And then examining the transaction, we can see that the first transaction occurs December 1st, 2010, and the last December 9, 2011. 1 year in duration, yeah. Daily transaction count shows, okay, the daily transaction count. Let's do this. Okay, so yeah, we have some, yeah, oh wow, yeah, you can see transaction. Here we have a peak, 218 transaction, and here we have close to, come on. Yeah, whatever. So you see, these are transactions. Beautiful. We can smooth this out a bit by summarizing activities by month. Okay, let's do this. January and July. So yes. Here we have a beautiful transaction in November and December. Remember, we have just 9 days in December. 9 days of December 2011. The last one was December 9, 2011. So this is clear that here it comes down on December. But this is a nice indication. So for a little more than a 1 year period, we have the data for 4,000 unique customers. And this customer generated about 22,000 unique transactions. Now this is nice. Yes, 4,372 customers and 22,190 transactions. Great. A little quick math may lead us to estimate on average each customer is responsible for 5 transactions. Instead, we count the unique transaction by customer and then examine the frequency of these values. We see that many of the customers have engaged in single transaction. Okay, the distribution of the count of repeated purchases declines from there in a manner that we may describe as a negative binomial distribution. Which is the basis of the NDB acronym. Okay, so here we go. The distribution of per customer transaction counts. Oh yeah, we can see it goes down. If we alter our last analysis to group a customer's transactions that occur on the same date into a single transaction, a pattern that aligns with metrics we will calculate later, we see that a few more customers are identified as non-repeat customers, but the overall pattern remains the same. Yes, of course. I don't know why we're doing this, but let's say, okay, we follow here the prepared notebook by Databricks. And thank you, Databricks, for having open source your demonstration notebooks. So focusing on customers with repeat purchases. Yes, we can examine the distribution of the days between the purchase events. Okay. What's important to note here is that most customers return to the site within 2 to 3 months of a prior purchase. Yeah, longer gaps do occur, but significantly fewer customers have longer gaps between return. Yes, okay. In the context of our BYTD model, is a critical time factor to determine whether they will come back, with the probability of returning dropping as more and more time passes since the last event. Now this makes sense. So what we do here, SQL distribution of per customer average number of days between purchase events. So what is it? Spark job is running. Yeah, running. Yeah, come on, let's do it. And here we go. The average days between the events. Okay, so we have a peak here at 22 days. This is interesting. So this is a beautiful distribution, exactly as we expect our Gauss distribution formula. So calculate now the customer metrics. Remember, we had 2, the frequency and the recency. consists of raw transactional history. Yes, in order to apply this model where we have the code, we need to derive several per customer matrices. Good. The frequency, the number of days on which a customer made a purchase, subsequent to the day of the customer's first purchase. Okay, easy. Age, the number of time units in days since the date of a customer's first purchase to the current date. Okay. Recency, the age of the customer at the time of the last purchase. Okay, this is simple. I mean, there's nothing else to do. You can follow the code. We have for each customer ID, we have a frequency, a recency, and the T is the age, the number of time units in days. As the lifetime library, as a single threaded Python library, yes, of course. Using this library to derive customer metrics on larger transactions may overwhelm your system. Of course, we have distributed capabilities of Apache Spark. Spark statement, SQL statement. Okay, yes, okay. I'm not interested in SQL right now. Just have a look at the procedure. Customer ID, the frequency, the recency, and the time, the dates, the number of dates. Capture the stats in a data frame and display the stats. This is done. We have our typical group by. Yes, this is beautiful. Of course, wait, Spark SQL does not require the data frame to be accessed exclusively using a SQL statement. We may derive the same results doing a programmatic SQL API Python. Yes, 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 yes. Align better with some data scientist preferences. Yes, definitely with my preference. The code in the next cell is purposely assembled to mirror the structure of the previous SQL statement. Okay, so everything we did here, we do now again in a programmatic SQL API. So whatever data scientist, this is it. Yes. PySpark SQL functions. Yes, we do import everything. We should get the same result. Display the matrix. Yes, again. Oh, let's take a moment to compare the data just to confirm the results are identical. Okay, leave this to you. Yes. Okay. Number 1. Number 2. Yeah, number 3. We don't have to render everything. So let's see, next point. The matrix we've calculated represents summaries of a time series of data. Yes. To support model validation and avoid overfitting of our model, a common pattern with time series data is to train models on an earlier portion of the time series, okay, known as the calibration period, and validate against a later portion of the time series, known as the holdout period. Okay, this makes sense. And the Lifetimes library that we imported and we use, the derivation of per customer metrics using calibration and holdout periods is done through a simple method. Because our dataset consists of a limited range of data, we will construct this library method to use the last 90 days of data as the holdout period. Okay, yeah, no problem. I think they know what they're doing. Should be reasonable. So our holdout is 90 days. Beautiful. Set this last transaction data as the endpoint for this historical data set. Okay. Calculate the required customer metrics. Yes, yes, yes. This is typical SQL. As before, we may leverage Spark SQL to derive the same information. Again, we examine this through both the SQL statement and the programmatic. Okay. Duration hold at 90 days. Yeah, nice, beautiful. We have it. We examine this through both. This means we have a SQL statement and the same. So let's focus on the Programmatic SQL API because I think this is what we are looking for. And here the equivalent programmatic. Yes, this is what we want. Spark job. Using some customer frequency, the recency, calibrated frequency hold and duration hold. Beautiful, 90 days. Maximum results limit. No, I believe you. We can verify these again the same. Well, we do think that this is done. Our data preparation is nearly done. Heaven's sake, it's already a quarter of an hour. So the last thing we need to do is to exclude customers for which we have no repeat purchases. Of course, yeah, the frequency is 0. Okay, the Pareto and the NBD and BGNBD models, we will focus on performing calculations on customers with repeated transactions. Yeah, of course. We don't want single events to take place in our model. Now, stick to the two popular of the models in use today. We will limit our data to align with their requirements. Yes, beautiful. Both the pandas and the Spark DataFrames are filtered simply to be consistent with side-by-side comparison. You would choose, of course, either to go with pandas, or if you have a Spark cluster, like I have, a Spark DataFrame for data preparation. So what we do is we simply remove customer with no repeat. So if the frequency is greater than 0. So done. Beautiful. Train the model. Hey, finally we have the model. To ease into the training of the model, let's start with a simple exercise using a specific model, the original model, where we use the calibration holdout dataset constructed in the last section, fitting the model to the calibration data, and later evaluating this model using the holdout data. Now this makes sense, no? Okay, so from the Lifetime Python library, we import the different models and the different whatever. I'm sure you know better than I do because I'm not a marketing specialist. Whatever they love to have with our models now fit. Let's make some prediction. We'll grab the actual for the same period and subsequent step. Beautiful. Yes. With actual and predicted values in hand, we can calculate some standard evaluation metrics. NumPy, score, mean square error, and root mean square error. Yes, beautiful. Let's do this. Our MSE. Heaven's sake, wow. Okay, while the internals of this model may be quite complex, in a nutshell, the model calculates a double integral of two curves. One, which describes the frequency of customer purchases within the population, and the other, which describes customer survivorship following a prior purchase event. Okay, yeah, this is clear. As simple as trading a model may be, we have two models that we could use here. The Pareto model and the BG model. The BG model simplifies the math involved in calculating customer lifetime, and it is popularized by the BTYD approach. Both models work off the same customer features and employ the same constraints. Okay, you choose your best model. Each model leverages an L2 norm, and this is a simple Euclidean norm, regularization parameters, arbitrary set to zeros in the previous training cycle. Which model works best? We should consider the value between 0 and 1 works best and give the British search. Hyperparameter tuning, you are familiar with this. I already showed you how to use MLFlow with hyperopt. Hyperopt allows us to parallelize the training and the evaluation of models against the against a hyperparameter search space. So we find, or this finds the best hyperparameter for us. We don't have to look for the best hyperparameters. This can be done leveraging multiprocessor single machine. Yes. Spark cluster. Yes, we have a Spark cluster, Tom7 up and running. A loss function is calculated. Of course, various optimization navigates the search space to locate the best available combination of parameters settings to minimize the value returned by the loss function. Well, of course, this is standard. To make use of hyperopt, let's define our search space and rewrite our model training and evaluation logic to provide a single functional call. which will return a loss function. Okay, you know this, just let execute it. Now the evaluate model function retrieves its data from the input, and the broadcasting variable, each worker in the Spark cluster, you know this. Let's perform our hyperparameter tuning over 100 iterations in order to identify the best model type and the L2 settings for our datasets. And here we go, MLFlow. Yes, finally we have MLFlow. My goodness. So we have our broadcast, our trial, parallelism, our workers. Yeah, we are here on the free community edition, of course. So yes. Hyperopt, automatic trials, and MLFlow. Yes, beautiful. This will take some time. 0%. Yay. Spark jobs. Oh, wow. MLFlow runs. Yeah. 12 runs to an experiment you can have here. Of course, if you want the details of the experiment, you just click here to get your data. But I just want to run through the whole process one single time with you, and then you can make a deep dive into each cell and optimize or adapt it to your specific problems. Okay, so we have now our Spark job is running, MLFlow is running. We have 100, yes, beautiful. Well, I suppose this is gonna take some time. So let's look ahead. When used with the Databricks ML runtime, did we have an ML runtime? The individual run that make up the search track built in a built-in repository called MLFlow. You notice I have a specific video on MLFlow for more information. Yes. The optimal hyperparameter settings during the hyperopt iterations are captured. Yes. And if we are done, we can have a look at the optimal parameter. Of course, we have to wait for the other cells to finish. And then we say, okay, now that we know our best parameter settings, let's train the model with these optimal parameters to enable us to perform some more in-depth model evaluation. And then we would start with this. So let's wait for the model to come to turn. Yes, we are running. Yes. Okay. 400 MLFlow runs. So I will be back whenever this cell will stop executing. So I see you in a second. And we are back. So you see, we have 100 runs, MLFlow runs, and we have now our optimal hyperparameter settings. For L2, we have this value and we have this model chosen. Beautiful. So now we can run this. Yes, beautiful. Yeah. And then we evaluate the model. Of course, you can have the evaluation now. It's a bit more challenging to interpret. We can examine how purchase frequency in the calibration periods relates to the actual frequency and the predicted. Okay, let's compare it. Oops. Oh, sorry. There's a display. We should get some. Oh, yeah, there we have some correlation. So in orange, we have our model, and in blue, we have the real data. Well, yeah, for a first run, it is not that bad at all. So what we see here is that a higher number of purchases and the calibration predicts a higher average number in the holdout period, but the actual values diverge sharply from the model prediction when we consider with customers with a large number of purchases. 60, yeah, at 60 is the last time they met, and then ciao, they go weird. Thinking back to the charts in the data explorations, and we might recall that there are very few customers with such large number of purchases, so that this divergence may be the result of a very limited number of instances at the higher end of frequency range. So we have not enough data for our most important customers. More data may bring the predicted and actuals back together at the higher end of this curve. Yeah, using the same method call, we can visualize time since last purchase relative to the average number of purchases in the holdout period. Yes. Okay, let's have a look at the time that we get from our model. Time since user made the last purchase. Again, in orange, we have our model prediction, which are real nice at the lower time period and higher. Yeah, there are some spikes, but you can see there's definitely some kind of relation. Plugging the age of the customer at the time of the last purchase into the chart shows that the time of the last end customer does not seem to have a strong influence. Yes, it's with any customers that stick around a long while are likely to be more frequently engaged. Yeah, okay. Let's have a look at this. Well, of course, yes. From a quick visual inspection, it's fair to say that our model isn't perfect, but there are some useful patterns that it captures. Using these patterns, we might calculate the probability of a customer remains engaged. So finally, we have our probability, and here's it. The probability. Wow. 0.99. Yes. Oh, 0.76. That's not so good. So you see for your specific customers, you got a probability. This is exactly what we have been looking for. Well, it is not optimal, yes, but I think it gives you a good idea. And the model, if you train it even further or even longer, maybe you can even increase the prediction accuracy. So, the prediction of a customer probability of being alive could be very interesting for application to our marketing process. But before exploring model deployment, we deploy the model. This is nice. Let's make a look at how this probability changes as customers re-engage by looking at the history of a single customer with modest activity in the dataset. So we have a customer named 12383. Okay. Yeah. From this chart, we can see this customer made his or her first purchase in January. Yeah, of course. January. Followed by repeated purchases later this month. There was about a 1 month lull in the activity during this probability of becoming alive, declined slightly, but purchases in March, April, and June of that year, the customer sent repeated signals that he or she was engaged. Yes, they're coming back. Yes. Since that last June, the customer hasn't been seen in our transaction history, and our belief that the customer remains engaged has been dropping. So as a moderate pace given the signals previously sent. Okay, so you see, yeah, it's dropping. Yeah, of course. How does the model arrive at these probabilities? The exact math is tricky. Whenever I read a sentence like this, the exact mathematical formulation is tricky, but by plotting the probability as a heat map, I see. Now comes color back to life. Okay, so yellow is probability 1. No, the customer's recency, probability customer is alive per frequency and recency of a customer, and 0 is dead. Okay. Historical frequency, yes, of course. So in addition to predict the probability of a customer still alive, you can number of purchases expected from a customer over a given future time interval. So what he will do in the next 30 days, we can predict this. Yes, of course, we have a model. We can do some prediction. Of course, we can calculate this probability for each customer based on their current metrics. Yes, beautiful. So here we have purchases predicted for the next 30 days. Okay, so you can clearly have a customer segmentation given the future probability of purchases in the next 30 days. So step 6, deploy the model. Geez, it's a long video. Deploy the model for predictions. There are numerous ways we might take use of this model. Wish to predict the number of purchases. Yes, all we make is a trained model. Yes. Challenge is now to package our model into something we could reuse. Yes, we use MLFlow in combination with hyperopt to capture the model's run during the hyperparameter tuning exercise. Yeah, as a platform, MLFlow is designed to solve a wide range of challenges that come with model development and model deployment, including the deployment of models as functions and microservice application. Yes, this is it. This is the nice part. So MLFlow tackles deployment challenges out of the box. Lifetime models are not included. So to use MLFlow as our deployment vehicle, we need to write a custom wrapper class. Yeah, which translates the standard MLFlow API calls into logic which can be applied against our model. To illustrate, we have implemented a wrapper class for our lifetime model, which maps the MLFlow predict method to multiple prediction calls against our model. We map predict to a single prediction, but we bumped up the complexity of the return to show that one of many ways the wrapper may be employed to implement custom logic. Just follow this recipe. I don't want to say anything else. Nice. Create the wrapper for your lifetime model. Beautiful. So let's do this. Let's see if it works. Yes, we need now to register our model with MLFlow. As we do this, we inform it of the wrapper that maps its expected API to the model functionality. We also provide environment. Typical log. Add lifetimes. Info. Save the model run to MLFlow. Yes, this is the nice part. Here we go. Running the command. Yeah, it's done. Logged one run to an experiment on MLFlow. Note that our model along with dependency information and class wrapper have been recorded. Let's use MLFlow to convert a model into a function we can employ against a Spark DataFrame. Finally, after half an hour. Heaven's sake, convert the model into a function we can employ against the Spark DataFrame. Our Spark UDF, you are familiar with this. I have a video on Spark UDF, so don't ask. Assuming we have had access to customer metrics for frequency, we can now use our function to generate some prediction. I hope we have some outcome now. Yes, come on. Yeah, here we have our customer. The probability is alive. Purchase 50 days, 30 days, and 45 days interval. This is nice. Jawohl. And then SQL, predict the probability this customer is alive and will return in 15, 30, and 45 days. Okay, again. Prediction. Here we go. So you can save it or you can have a look at this. Yeah, it's not. Hey, wow. So this is exactly what we have been looking for. And now the last part with our lifetime model now registered as a function. Yes, we can incorporate customer lifetime probabilities into our ETL batch, streaming, or interactive query workload. May also be deployed as standalone web services, leverages Azure Machine Learning or AWS SageMaker, whatever you prefer. This is it. This is customer lifetime. Yes, we have it. MLFlow as a function. Isn't this beautiful? Now, of course, the link to the notebook, this is all credits go to Databricks. This is an official Databricks notebook because they know what they are doing. They have this accelerator beautiful log that we just used here. I run with you operational here on a Spark cluster with you through everything. Everything is up and running, operational for you to input your data of your company. And then you get some very nice probabilities if you want to predict the future behavior of your customers. I say thank you for the first video of this, and the second video coming up in some days. We will increase the complexity and show you what you can do if you have some added value to this. I say thank you, and I see you in the next video.